Hello, everyone. Welcome to today's webinar. I'm Ann Thayer, contributing editor to the CNEN Media Group, and I'll be moderating today's event. This webinar is titled A Useful Method Development Strategy for Reversed Phase LC Separations of Large Protein Variants in Reversed Phase, and it's being sponsored by MacMod. CNEN works with sponsors to identify topics of interest and value to CNEN's audience, and consistent with CNEN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. Before we get started, I'd like to cover a few technical details. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget at the bottom of the screen or type your query into the Q&A box. If you're disconnected during the webcast, please log in again according with the instructions you received earlier. You're encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I'll be posing as many as time permits. Please note that CNEN does not endorse any company, products, or services that may be mentioned in the webinars, and that each webinar will be archived at CNN Online after the webcast. The presentation today is being sponsored by MacMod. MacMod's mission statement is Smarter Chromatography, which means that it partners with customers to offer innovative solutions to complex problems. The company uses advanced analytical software to match its product portfolio with a customer's separation needs. It leverages 30-plus years of experience in the LC column business and its technical expertise and manufacturing network to help solve application problems. And it provides up-to-date and accurate technical catalogs and reports from leading separation scientists to keep clients informed of new technologies. During the presentation today, we'll hear from Benjamin Liebert. Ben is an associate scientist in R&D at Advanced Materials Technology in Wilmington, Delaware. Prior to joining AMT, he worked at Insight, supporting drug metabolism and biopharmaceutic LC-MS assays. He brings over a decade of product development experience in separation science and is specialized in research analytical testing and quantitative LC-MS analysis in support of biopharmaceutical, environmental, food, cosmetic, and crop science. He received his degree from the College of New Jersey and is an active member of the American Society for Mass Spectrometry. I'll now hand things over to Ben.
Thank you, Ann. Thank you, everybody, for being here today. We're going to be talking about protein separations and using the large pore, superficially porous particle. First, I'm going to start talking about some particle characteristics, some history behind the particles that we make here at Advanced Materials. And then I'm going to go into some options for improving protein separations by reverse phase. So we'll talk about stationary phase options and some mobile phase ideas. So the superficially porous particle technology has been known for quite a while now. You can see the patent here is established in 1967 by Jack Kirkland, who up until recently was working at Advanced Materials. This invention is the basis for which these particle technologies that we're going to talk about come from. The patent describes a novel packing of these superficially porous particles, and it's essentially what we're going to be discussing today. And that diagram on the left more or less lays out what it looks like. You have a solid core surrounded by a layer of microparticles that are bound to the surface. Advanced Materials came out with the superficially porous particle 90 angstrom material back in 2006. You can see the diagram or the graphic on the left shows the 1.7 micron core, which is surrounded by the pore shell, which is a layer about 0.5 microns thick. And to the right is the SEM of that particle. Fairly similar to the graphic. These particles were, being used for small molecules, and they exhibited low back pressure due to the particle design, So there wasn't a need for specialized HPLC equipment. And we're maintaining high resolution at higher flow rates due to the flat C term in the Van Teenter plot. But when you move from small molecule up to something bigger, say perhaps a peptide, there was something that was being realized about what we needed to get from these columns in terms of the efficiency that we were looking for. The plot on the left is on the y-axis you have reduced plate height, and you have mobile phase velocity on the x-axis, and this is a demonstration of the efficiency that you would see for a small molecule on two different pore sizes. This is a 15 nanometer pore versus a 9 nanometer pore, and the efficiency remains the same for the small molecule at higher mobile phase velocities. However, once you get into a larger molecule size range, say for example the beta amyloid, which is about a 4,000 Dalton peptide, you begin to see a drop-off in column efficiency on the 90 angstrom material. When you open up the pore to the 160 angstrom size, that's when you see that you regain some of the efficiency that you lost with a smaller pore. And in fact, at 2 milliliters per minute, you get about threefold lower reduced plate height for that 160 angstrom pore. So what are the needs for large biomolecule separations? Well, one, your pore size must fit the molecule size. Restricted diffusion limits the efficiency and the load capacity. So, and peak capacity effects by kinetic and retention limitations must be, respected. Particle morphology must be optimized for surface area and volume. So the shell thickness must be catered to the right size so that the diffusion path and the surface area are respected as well for favorable separations of these larger biomolecules. And particle distribution as well is important, as well as the surface chemistry on these particles. So around 2013, Advanced Materials came out with a wide pore, 400 angstrom, 3.4 micron particle. So this is a substantially large solid core relative to the surface, shell. Many variations of this particle had been gone through in the development process to try to get the optimal separation performance for these proteins. The idea of going to the larger pore is essentially where we're headed to do these larger biomolecule separations. And in this example of a separation of a monoclonal antibody that had been IDES digested, this is being run on a 400 angstrom halo protein C4 column. We're seeing on the top panel, the plus DTT is the reducing condition in which you get 3 fragments from this, and on the bottom panel you have the non-reducing condition in which you get the 2 fragments, the FC portion and the FAB portion, and you can see that we're getting relatively sharp peaks and resolution of some of the variants in this particular digest. Another monoclonal antibody separation run on a 400 angstrom C4 is this trastuzumab separation on the left panel, and this is a UV trace of a separation of light and heavy, and you can see that the peak performance is looking good in this example. On the right panel, you have an MSQC8 antibody drug conjugate mimic separation in reverse phase. And you can see here on the 400 angstrom, we're getting resolution of the variance of depending on the drug load on this particular protein. To take it one step further, we moved from 400 angstrom to 1,000 angstrom in 2017. Advanced Materials came out with the 1,000 angstrom pore size superficially porous particle done on the 2.7 micron particle design with 0.5 micron shell thickness. The surface area was about 22 meters squared per gram, which is reasonable, and the whole purpose of going to this size was to create a design for a particle that would be optimal for larger proteins. Densely bonded with C4 phase with end capping, and it's high temperature and low pH stable. Now, why do you need larger pores than the size of the solute? It's been long recognized that the diffusion of molecules in pores is slower than diffusion in bulk liquid. This leads to more zone broadening through resistance to mass transport within the stationary phase term of the plate height equation. And theories have been developed which account for this effect in idealized pore shapes, cylinders and slabs. In the graphic to the left, you'll notice on the y-axis is the psi p term, which is the hindrance factor, and psi p scales with dp, which is the diffusion of the molecule into the pore. On the x-axis, you'll see the lambda m, which is a ratio of the radius of the molecule to the radius of the pore. So as you see, as the radius of the molecule approaches about half the size of the pore, the diffusion into the pore is being restricted. As you increase the size of the pore relative to the radius of the molecule, that molecule has more access into the pore, and the diffusion of the pore will therefore go up, as exhibited there. And there's ongoing efforts to examine these fluid mechanics and transport properties of these superficially porous materials. So let's take a look at protein separation. This is a series of separations done using 4 proteins, comparing fully porous particle technology in the upper left-hand panel. This is a 1.7300 angstrom fully porous particle separation, and you can see as we go to a larger, or as we go to a smaller pore size on the panel below it, the halo 2.7, you do take a hit in your peak width, especially towards the end. The later eluting larger the larger proteins, phenolase and carbonic anhydrase, are co-eluting. However, as you move to the 3.4400 angstrom, you begin to see that compared to the fully porous particle, we're actually seeing better performance in terms of the peak width on each of these in each of the instances of these proteins. We're also gaining retention as well. And as you move to the 27,000 angstrom material, not only have we gained performance in terms of the peak width, so a reduction in the peak width at half height, but we're seeing additional gain in retention. So we get improvement in peak width and retention for the larger pore, superficially porous particle. And as the protein size increases, the peak widths decrease with increasing pore size. And these results have been also observed for TFA as well as DFA. Now, as we take a look at a larger biomolecule, in this case a separation of trastuzumab, we can compare the effects on a fully porous particle versus that of the superficially porous particle. Here we're looking at a 300 angstrom separation versus the superficially porous 400 angstrom and 1,000 angstrom in the green trace at the bottom. So not only are we gaining retention on these larger pore size materials, but we're increasing performance in terms of the peak width at half height. And 1,000 angstrom at 0.1 minutes is by far the best in this example. When we look at this advantage, it's not unique on the superficially porous part. It's not unique to one monoclonal antibody. Here, this chart is comparing the performance of a 1.7 micron 300 angstrom to that of a 2.7 1,000 angstrom material. In each case, for trastuzumab, ciliumab, and 3 other antibodies that were obtained through a collaborator, the peak width at half height is exceedingly lower in every instance on the 1,000 angstrom material versus the fully porous 300 angstrom. Now, what happens when you adjust the flow rate on these materials? The speed and, well, time is of the essence, and if you can, you want to speed your analysis up to within reason to have, reasonably performing analytical methods. In this case, we're comparing the 2.7 micron 1,000 angstrom to the 3.4 400 angstrom, and then the fully porous 1.7. The y-axis we have peak volume, which is just another way to measure the efficiency or the performance of these, in this case, trastuzumab on these columns. In this case, it's quite apparent that not only at low, but at 0.1, 0.2, 0.4, all the way up to 0.8, the superficially porous materials are performing more efficiently at every flow rate and quite evenly across all flow rates in terms of their efficiency, as opposed to the 1.7 fully porous 300 angstrom material, which all the way up to 0.8 has a peak volume 3 times or almost 3 times that of the superficially porous materials. You may be interested in the load effects and on the column performance. And in this case, we compared the 1,000 angstrom, 400 angstrom materials to the fully porous 300 angstrom 1.7. For larger molecules, large pore, superficially porous particles tolerate large sample masses effectively. And this performance loss is progressive, and it occurs around 20 to 50 micrograms. It is important to note, though, that at all load levels, the 1,000 angstrom pore size particle performed best for this particular monoclonal antibody, which is trastuzumab. So we've talked about some ways in which the particle structure and how you can adjust it to change the effects of your performance for your particular protein of interest. Another way to do or to improve your separation is to manipulate the mobile phase, your bonded phase, and your operational temperatures. Many molecules of interest actually are inherently heterogeneous, and the reverse phase will not resolve all the variance. So we're going to manipulate and optimize additional parameters other than the particle to obtain optimal separations. In this table, we're looking at 3 different bonded phases that are offered on the 1,000 angstrom pore size material. diphenyl, C4, and the ESC18 bonded phases. And here are listed the retention factors for the separation of phenones and uracil. You can see that the retention factors vary across the bonded phases, as do the selectivity factor, Each of these phases are highly similar in terms of their efficiency, tailing factor, and like I said, they exhibit different tension factors and selectivity. The diphenyl phase has been characterized using computational models. These were done in-house by Mark Shore, who some of you may be familiar with. The idea was to understand how this phase may be interacting with these larger biomolecules. These phenyl groups are not coplanar, which may be sometimes this phase can be confused with other bonded phases, but in this particular computational analysis, the phenyl groups form a favorable van der Waals surface, or a pocket for these biomolecules to interact with. And the rotation around the C2 silicon 1 and the C8 Si1 bonds will accommodate the larger molecule fragments. So in this example of a separation of 4 proteins done on 3 different phases for the 1,000 angstrom superficially porous particle, it's important to note that the retention of these proteins across the bonded phases may not correlate to small molecule retention, and there is no global pattern to be observed. The idea is that if you're going to run an analysis with a particular protein, it's important to know that you may need to run that and compare across a variety of phases, because predicting its retention and its separation characteristics is very challenging. But in this particular case, you can see that the selectivity differences allow different separation choices for these particular proteins. You are afforded some retention increases. For example, diphenyl, you see some retention increases, in addition to a resolution of some of these minor peaks that you're seeing on the sides. Particularly, I'll point your attention to peak number 2, the lysozyme. Diphenyl is showing resolution of those peaks, as well as some increased character or definition of the peak at the tail end of the enolase, as opposed to these other phases. So we tested the stability of this diphenyl phase under fairly aggressive acid and gradient conditions. And it was observed that after 4,000 column volumes, we only saw a 5% decrease in retention factor for small molecules. So the results support that the diphenyl phase shows increased resistance to hydrolytic attack, the siloxane bond to the silica surface. So, what are the effects of the bonded phase on separations of trastuzumab? So here, this is an overlay of 3 different bonded phases, also being compared to the fully porous particle, 300 angstrom material. We do see an increase in retention for diphenyl. Then the retention is often diphenyl has the greatest retention, followed by C18 and then C4. You do see on the tail end of this antibody separation selectivity differences in terms of the variance. And you get similar peak widths for each of these bonded phases, as opposed to the less efficient and more less defined separation that you would get on this fully porous particle. Now, I'm going to take a couple minutes to talk on this slide. This is a fairly important slide. Temperature dependence is key to understanding some of these effects that we see on these superficially porous materials. On the left graphic, you'll see this is a percent recovery study of this was done with trastuzumab and nismab, and the black trace was an analysis that was done on a diphenyl phase, and the blue trace is an analysis done on a C4 phase. The idea here is that you have to be observant of the temperature that you're operating at to maximize your recovery on these materials. We observed that not all monoclonal antibodies require temperatures that are greater than 70 degrees, but in this case, if you're operating in a mobile phase that's acetonitrile, that the recoveries drop off below 70 degrees for nismab and trastuzumab. However, if you adjust the mobile phase to an acetonitrile and propanol mixture, you're able to gain back some of that protein loss that you saw and recover more of your protein off the column in each analysis. The panel at the right shows that your recovery does tick up even at lower temperature. In particular, I'd like to point your attention to the diphenyl performance at lower temperature, which seems to have a slight advantage over the C4 in this case. So the ESC18 also yields similar results to the C4 bonded phase for recoveries. The diphenyl exhibits a lower temperature for full recovery of these monoclonal antibodies. Like I said, not all MABs require greater than 70 degrees for the highest recovery in acetonitrile. Many of these MABs show lower temperature for high recovery. The reason why 50% acetonitrile and propanol was chosen for that right panel study was done because we didn't notice significant effects by varying that percentage of the percent composition of the mobile phase. And the similar patterns of recovery are observed for IgG2 separations, which were examined. There is a word of caution for going to higher temperature. In this case, a nismab analysis was done, and this separation was compared across 3 bonded phases, and it was compared on the fully porous C4 300 angstrom material. This star denotes an artifact that was observed. Upon reinjection of the main peak, this artifact was generated. But depending on what temperature you operate, it may or may not be present. At or below 60 degrees, it was not apparent. So, a word of caution: artifacts like these may be observed. So, operating at and it's unknown what it is. We have not characterized it, but it is curious and also a word of caution. Selecting temperature may be very important for the separations that you're pursuing. So we've talked about some mobile phase effects. We've talked about particle structure, temperature. Now we want to talk about some mobile phase additives that may give you some more ability to optimize your separation on these materials. For one, you need volatility for a particular additive. For those of you who do LCMS, you know that you do not want to plug your source. You need something that's low pH, something that's sufficient in terms of its ionic strength, which appears to be, beneficial for separations, and something that won't suppress your ionization as well. So we did a study of a variety of mobile phase acid modifiers. We did some initial selection, and the idea that we've been pursuing lately for quite some time now, for years, has been the idea of replacing the acid modifier for the more suppressive trifluoroacetic acid with something that would give us performance, but may not be as ideal as formic acid. In this case, this is a tryptic digest separation of enolase, and you can see that this is a total ion current chromatogram. On the bottom panel, you see the hit that you take for peptides in terms of the suppressive effects of TFA, whereas you do gain back some of that signal and maintain the efficiency in terms of peak width that you would see with the DFA. This was also looked at for synthetic peptides, and again, similar performance was observed. On the top panels are UV traces, and the bottom panel is the total ion current for the mass spectrometer. You can see a similar case where you get suppressive effects with TFA, and the DFA on the right is, you're maintaining your peak widths, and you also have some signal for these peptides. But once you move over to proteins, you take a little hit in terms of the ionization. However, you're able to maintain the column performance with these additives. On the left panel, you're looking at a UV trace in 0.1 TFA on the top, 0.25% formic acid, followed by 0.1% DFA, and 3 FPA acid modifier in 0.1%. On the right, you can see in TFA you have suppressed the signal that you're getting in the mass spectrometer. You gain it back with formic. In 0.1 DFA, you do see an uptick in ion intensity. However, it is slightly more suppressive for these proteins than it was for the peptides. So one development approach, now that we've been able to look at the acid modifier options, we've looked at temperature effects. Now we want to figure out how can we optimize based on the bonded phase options that we have, and all of these parameters. Now there's two approaches that are presented here. On the left is a column-based approach, and on the right is another approach that we can take using temperature and mobile phase composition. So I'll start on the left. In this case, this is a separation. This is a separation of an antibody where we have varied the bonded phase and compared it for the same antibody. You've gone and looked at different temperatures for this particular analysis and found something that works. So you're getting resolution of these variants, and now what you want to do is, once you've honed in on where you think you have a good separation, you can adjust your retention by adjusting the mobile phase gradient. And for the bottom B panel, you see here that we have a C4 versus this diphenyl phase. You can adjust it so that the center of the peak sits right about the same retention time as another phase, and pick whichever separation you like the best under those conditions. Another approach to do this is to take a fixed bonded phase and adjust the temperature. And you can see on the top A panel that as you vary the temperature, you're getting resolution of the variance on the tail end of this main peak. In this case, 60 degrees was selected. Then, once you have your temperature, you can move on and adjust your mobile phase, organics, or you can vary your acid modifier. In this case, acetonitrile TFA was compared to acetonitrile and propanol plus TFA, and then acetonitrile and propanol plus DFA. And due to the reason that we talked about earlier, the suppressive effects of TFA, DFA was chosen for this particular analysis, and then the gradient was optimized for time and convenience. One aspect of understanding these biomolecules is understanding where the variants are modified, and for the purpose of bioprocessing and qualification of these industrial processes. So in this case, we're looking at an IgG2, which in the literature has been claimed that disulfide bridge variants are partly to blame for, are responsible for the variation that we see in terms of the variance in this particular separation. So analysis of those variants is required. Many proteins possess the disulfide bridges and may also have free thiols. So in the case of IgG2, free thiols are formed during the conversion of IgG2 disulfide variants, isoforms. Maleimides are one convenient reagent for attaching a label to the free thiols in order to enhance the separation in the effort of understanding what these variants are. And this approach was described recently, and we employed it to do an analysis of the IgG2 using this labeling method. In the top panel on the left, so we're looking here at the labeling of trastuzumab, and we're concerned with what are these variants on the tail end. Can we enhance this separation somehow? And what we did was we did a labeling with N-tert-butylmaleimide. The top blue panel is a control without the label. And then when we added the maleimide labeling reagent to these, to understand the site-specific disulfide variant, we were able to pull apart a variety of peaks, which we did post sample preparation, in which we took those peaks that are labeled F1, F2, F3, and so on. We pulled those samples out and labeled them individually using sample prep, and then re-injected them to try to figure out what was happening in this complex labeled sample. And we were able to make some confirmations as to what we were looking at. The LCMS does reveal that the late peaks are within 3 to 11 AMU of the native IgG, and the labeling was conducted on the whole IgG and the resolve fractions, which enabled us to do some of the retention identification and deconvolution of these materials. The B and G labeled in red, we were able to identify these as not shifting in retention and had similar deconvolution results. So we are believing that they are not they're not possessing free thiols. whereas each of the others are possessing at least one, if not more than one, two, if not more than, sorry, I should say, one pair, if not more than one pair of the N-tert butylmalamides. So that was an interesting analysis. To summarize, improving protein separations is both practical and chemistry. So stationary phase modifications and mobile phase modifications are required for this type of separations optimization. The superficially porous particle silica packing material has provided superior separations. The 400 and the 1,000 angstrom pore size show particular utility for proteins. They are robust and they are routine. They allow for faster protein separations with higher efficiency, as opposed to the fully porous 300 angstrom materials. Subtle but useful differences in selectivity are available, and additional bonded phases are available on the 1,000 angstrom pore size. C4, diphenyl especially, and C18. For protein analysis, temperature optimization is crucial to maximize recovery and selectivity, but diligence is required to avoid artifacts in the example of the higher temperature analysis. The work continues on optimizing the pore size and the geometry for silica SPP, and the endpoints will be defined by careful analysis of the resolved protein samples with limited guidance guaranteed from small molecule analysis. And the more resolution gained with these newer reverse phase materials, the greater detail that we can obtain on subtle structure variations in these proteins. I would like to finish up by acknowledging the collaborators and AMT management, and I thank you for your attention. Now I have some poll questions, which I will submit. Anne, are you there?
Yes.
So I want to engage the poll question. Do I have to submit this question for it to work?
I think it should just appear on the live view. Yes, I see it on the live view. I think you just need to ask the question and let people submit their responses.
Okay, yeah, so I'm going to throw up some poll questions here. Would you be interested in a personal consultation for development of your biotherapeutic method utilizing the new Halo BioClass 1,000 angstrom columns? Okay, and the next poll question. Are you interested in using a 1,000 angstrom column for biotherapeutics in the future? Oops. And now I think we're going to start with the questions and answers if you're all finished with your questions. Or your poll questions, I should say.
Great. Thanks, Ben, for your very interesting presentation. And you're right, we'll now move to the Q&A. We had some questions that came in during your talk. The first one is, where is the protein going that is not recovered in the recovery comparisons versus temperature? What happens to recovery with repeat injections at each temperature?
So it's definitely sticking to the column. Where is it and how is it interacting? It's difficult to say, but due to the nature of the separation, it is most certainly being stuck to the column and may not come off at all. What happens to the recovery with respect to the injections at each temperature? Repeat injections. Yes. Repeat injections, recovery. I can't say exactly what would happen in the case of any particular protein that you might be working with. My observation over the course of time with these, my experience with these particular proteins, especially trastuzumab, has been that recovery is consistent over time. But if you're looking for precise analysis, that's something that you should probably look at for your particular protein, as they do change in terms of their characteristics. As you saw in that one slide, there was variability in terms of going from trastuzumab to nismab on 2 different phases.
Thank you. Someone asks, at temperatures greater than 70 degrees centigrade, the protein molecule will degrade into so many fragments. In such cases, how do you identify the parent molecule?
Well, you might want to go down to lower temperature. Let's see, is this one, is protein going? I'm on the, all right, so I got to look at the top one. No, that's not it. Here it is. All right, now I'm looking at the question. If you're concerned with fragmenting your analyte or your biomolecule of interest, you may have to go to lower temperatures, in which case, due to the temperature effects that were shown in terms of if you're concerned about peak recovery, 60 degrees with a modified mobile phase of N-propanol acetonitrile using the diphenyl phase was reasonable in terms of its column efficiency and recovery. So that's one way to get around this high temperature fragmentation if that's something that you're concerned with. So I would recommend to just go to lower temperature and work with a mobile phase system that provides you with reasonable recovery for your experiment.
Okay. Another question is, how does the HALO 1000 columns compare to SEC for monoclonal antibody analysis?
Well, SEC, you're operating under different conditions. I would say that you should know what you're trying to achieve by doing the separation. So in the case of SEC, I know you're under less denaturing conditions, perhaps, but in terms of reverse phase separation on 1,000 angstrom material, it may be more amenable to different types of detection. For example, if you want to do electrospray, reverse phase may be more favorable for that type of an analysis. It really just depends on what your goal is to achieve. Let's see. How does it compare to SEC? Performance-wise, it would depend on the mAb that you looked at. Of course, we see different variant efficiency in terms of the resolution and separation on different mAbs. But as you saw in that one panel where 5 of the monoclonal antibodies were compared, the performance was consistent across them. As far as SEC performance is concerned, I don't have that much experience with it, so I couldn't say exactly.
Someone asks, what is the limit for kilodaltons?
In terms of the mass, what is the highest mass you can go to?
I think that's what they're at.
I mean, we've done very large biomolecule separations of hundreds of kilodaltons on these materials. I think the limit is something that that we haven't fully fully understood yet. What's possible? So I think that if you have a very large material in mind of doing a separation on, perhaps we can work with you to figure out what is possible. Otherwise, I would say just try it.
Someone asks, what will be the typical number of injections for a purified monoclonal antibody on a column under regular conditions before any changes in profile or resolution?
All right, which one is that? Can you help me figure out which? I'm looking at the list here.
It's the top question on the list.
Top question? Okay. What will be the typical number of injections for purified MAB on a column under regular conditions? Well, you'd certainly have a lot less problem with a purified monoclonal antibody than, say, a dirty production, right off the line or right out of the kettle type of sample. Yeah, so this question gets towards a rugged, how rugged or how robust and stable are these? Again, it truly does depend on a sample-to-sample basis due to the complex nature of these proteins. These are robust columns in terms of their ability to handle sample load, like we've shown, and we have gone up to large injections of purified monoclonal antibodies in experiments on these materials. As far as the injections go, I can't put an exact number on it, but it's they are capable of handling a multitude of injections. That's what I can say to that.
So someone asks that they've previously heard that the diphenyl phases are not stable. Can you comment on this and how your material may be better?
Yeah, there was a slide in particular where the idea of stability was tested under aggressive gradient conditions and under a 0.2% TFA acid condition for 4,000 column volumes, and only 5% decrease in retention of the small molecule was observed. So I think the stability has been tested for the diphenyl phase.
Someone asks whether Halo is good for purification of insulin.
I can't say that I know if it's good for insulin purification because I haven't done that. That would be something that you might want to talk to us about. I can't say for myself if it is.
I think we'll do one more question, and that is if pore size is important, why is the separation I see in my 1,500 angstrom product not adequate?
1,500 angstrom is fairly large pore size. It's possible that it's too large. I couldn't say exactly why you might require that large of a pore size to do your separation, but that's something that we're willing to engage with you about if you are curious about what type of particle size is actually desirable for your separation.
Well, thank you, Ben, for answering all those questions and for your fascinating presentation. I want to thank all the participants for being a great audience. Be sure to check CNN or CNN Online for information on the next edition of CNN webinars. Thank you On24 for technology and production services, and thank you MacMod for the sponsorship that made this interactive webcast possible. For CNN webinars, I'm Ann Thayer. Have a good day.
Thank you, Ann.